So much energy. The reorder of people's yeah, lower that. Oops. It's good.
Okay. Hope you all had a good break. We're going to start off and we're hopefully going to finish off a bunch of the microarchitecture memory side stuff today or this week, which should represent close to what we need for the exam. And at that point, I'll set the date for the midterm. It'll probably be an evening exam sometime in April, but I'll figure that out in the next week or so. Okay. I just wanted to, bring, who's heard of this? Blackwell, did anyone hear this announcement? So some folks, right, and sort of keeping up with the latest and greatest, announcements on future generations. So Hopper is sort of the current NVIDIA generation of GPU. They just announced that the next one is Blackwell, right? So they keep sort of the machine rolling. And it's highly focused on AI, as you might expect, right? They have a bunch of different updates to various things throughout the microarchitecture to try to help AI run better. And then they have all these quotes from all of these CEOs that are going to continue to buy NVIDIA GPUs for the most part for running AI. I hope to get to some of the newer stuff like the Tensor Engine and a little bit more about the details of the Tensor cores, which that isn't in the online material because that stuff is sort of newer. But I'm not going to talk about anything specific here, but it sort of just shows you that it just keeps rolling. The chip just keeps getting bigger. Okay, the peak tops just keeps getting higher, and the precision just keeps getting lower. Right, so the Tensor cores in the Hopper, they supported FP8, right? Now they're going down to FP4. And that's a good way to double your throughput because you don't need half as much information to do the same amount of work. And as long as the ML models can tolerate these lower levels of precision, particularly in inference, then you can keep doubling everything by just making the precision smaller. And we're still getting huge amounts of more transistors, right? There's probably some kind of chiplet stuff going on inside this thing to help it scale to the size that it is. I haven't had time to actually read this through in detail, but I'm just alerting you to this. I'll post this on Piazza as well. It's sort of like just showing you that this is, moving. This sort of big train on latest GPU generations just keeps moving. Questions on this? Anyone read this in detail and have any insights or anything that seems super interesting? For the most part, they're doing the same thing, just more of it. Yeah.
They just combine two chips together.
Right. Yeah. Basically.
I feel like the only interesting part is the compiler optimization for LLM.
Yeah. Well, all of the Tensor Engine stuff, you mean? Or what? Something else? You don't know.
Yeah, more on the compiler side.
Yeah. So the software stack continues to march on. The hardware itself, it doesn't really change all that much, except you get more of it and the precision falls generation to generation. But, it has good sticker value in twice as many or 4 times as many tops or whatever, however they want to count it. So, most of the stuff that we're learning here, even though it's based on GPUs that are a little older, it's all still the way it works in these newer generations. There's just more of it. All right. Let's move back to here. Any other comments on this? Yeah.
Would it be more, like, if you want to do something with higher precision?
Yeah.
Would it still be more often use an older version, like Hopper, or would
No.
you use a newer one and just like expand the number?
No, you're still better off using the newer one. Right. Transistors, it's still better implementation technology. The chips are still larger. I mean, cost-wise, is probably not better because the premium on these is insane if you can even get one. But just in terms of raw throughput, hardware companies always have this problem. They basically make their previous generation obsolete when they release their next one, particularly for the high-end stuff. If you're smaller models or whatever, you can probably still get away with a V100 or an A100, right? And it's cheaper. But when you're talking about selling these to Amazon or Facebook or Microsoft, they're all in a war against each other for the best AI, and they all need the latest machines. So they'll all probably buy as many of these as they can get their hands on. But you're right. It doesn't, there's usually no benefit to use the older one other than cost, typically. Other questions? All right. Okay, so people probably don't really remember where we were, right? So I'll just briefly give you an overview of where we were. So we were going through, we sort of gone through the microarchitecture. We talked about the different, scheduling mechanisms inside this thing, and then we were going to dive into the memory system. And we started diving into the memory system by taking a look at the L1 data cache and the shared memory. We talked about how these things can actually be shared in the microarchitecture itself. And we were sort of walking through what happens in this structure. Okay, this is lifted from a patent, okay, from NVIDIA on sharing the shared memory and the L1 data cache, and sort of walking through how this works. When you're doing shared memory accesses as well as when you're doing global memory stores or global memory loads, et cetera, or local memory or anything that sort of goes through this L1 data cache. And as we mentioned before, these things get partitioned when you spawn the kernel, right? So you have a fixed. So what is precious here is these arrays. Okay, these are the arrays of the data itself. That is represents the on-chip SRAM storage that you have in your GPU. And this gets cut up when you spawn your kernel based on how much shared memory you're using. So if you're using half of this as shared memory, then it's not. Sorry. All right, let me do this. Give me a sec. Okay. Right. So like this stuff, this is the precious stuff. Okay. This is but it's the bulk of the sizes. This is the SRAM. And when you spawn a kernel, you will subdivide this between however much shared memory you need based on how many thread blocks you have and how much shared memory each of them needs, and whatever's left over. Whatever's left over becomes the L1 data cache, and then you use the portion that you've sort of statically, it's not really static, but you sort of partitioned at the beginning of the program for your shared memory. So you might end up in a case where this much of it is used for the SHMEM, if you're using a lot of shared memory, and then what you're left over with for the L1D is this amount. And this is determined dynamically. You used to have to program this yourself, but now it sort of figures out how much shared memory you need and then just gives the rest of it to the L1 data cache. And so that means that this unit needs to be able to operate both on loads and stores to the shared memory, as well as loads and stores to just any global or local address that is going to be cached in your L1D. Okay, questions on this? Again, hopefully this is review just to bring you back to where we were before the break. So then we started to walk through how each of the individual memory accesses works. So this is a shared memory load. So, basically the issue scheduler will send it down the load store unit pipeline. Load store unit pipeline has, a given number of stages. We're assuming in this in this setup that there's a coalescing unit inside the load store unit. What does the coalescing unit do? What does memory coalescing mean on a global load? In the context of GPU instructions. Okay, nobody? Anyone want to try?
Does it do something like shuffling the memory to different?
No, not really. So I have one global load instruction, that's the warp instruction, and I perform memory coalescing on it. What does that mean? Yeah.
Like putting together multiple memory requests so that can bring together a proof of it.
Exactly. So remember when we were learning how to program in CUDA, and I said, try to make sure your accesses from parallel threads are beside each other in the memory system. The reason for that is we group together those threads into a warp, and then every address that every thread is touching could represent a different cache line access if they're touching stuff that's really far apart in memory. So the coalescing unit inside the load store structure will take all of the 32 addresses that are associated with this warp instruction, right? Because there's 32 threads inside of it, and it'll figure out what is the minimum number of cache accesses I need for those 32 addresses. So the absolute simplest case is where all 32 threads are accessing the same float, okay, the same 4 bytes. So now I only need to get that 4 bytes back, and then I've got the address, I've got the data that I can fill into all the lanes register files, right? And the other simple case is if they're actually, has this very regular pattern where thread 0 wants address 128, and then thread 1 wants address, 132, right? They're just offset by 4 bytes each. And then you go do one, if the cache line is 128 bytes, right? 4 by 32, assuming that most loads are 4 wide, because floats are the most common thing. Then you just need one tag access to go say, I need to service all of these 32 threads with this one access. So the coalescing unit is performing this reduction, where in the beginning, it looks like every thread needs to do its own memory access, but it actually doesn't. We're trying to minimize the number of memory accesses that happen at the L1D to basically maximize the throughput of the L1D. Okay, this is GPU optimization step number 1, usually. If you have a super diverged access pattern, your L1D and your main memory system are going to just be slammed with all of these access requests. And if you can sort of minimize that by having parallel threads do parallel work, then you usually get a lot more efficiency out of the system. Okay, that's what the coalescer does. Questions on that? Just a good warm up, right? To remember what the hell we're doing here. Thank you for answering the question. All right, so the assumption here is that there's some coalescing logic that's taking all these addresses and smashing them down to the minimum set of addresses that I need. And let's assume, for the sake of this example, that my cache line is 128 wide. So I have one tag associated with every 128 bytes of data. So out of the load store unit, I've got all of this, all of the different addresses that I sort of breaks down into. Oh wait, this is a shmem, sorry. So the coalescing occurs on the global memory accesses. What we're talking about right now is the shared memory accesses, but there is no real coalescing because, there's no tag check for the shmem, right? It's just direct addressing. It's like, I want to go to this particular location in the shared memory, so I don't need to do any tag lookups. So if we use doing a shared memory access, instead of having coalescing, we have to find the bank conflicts. Because remember, this was the other optimization step we did in CUDA. We had to try to make sure that we were accessing different banks from our shared memory accesses. And bank conflicts, we're going to have to serialize the accesses to this SRAM array because we can't in one cycle service 2. Okay. So the arbiter will figure this out. It'll know the conflicts are pretty easy to pick out. It's just a simple modulo operation because you know that it's strided at 4 bytes across 32 banks. That's sort of the definition of what the shared memory does, and that's what happens in this particular setup. So it'll try to find all the conflicts. If there are no conflicts, then it will just keep going, or if there are conflicts, it'll just let the non-conflicting ones go. So it could be that, let's say we have, a two-way conflict where every second thread is touching, is skipping a bank, right? So then when it wraps back around, you're going to have a conflict on 0, a conflict on 2. Like if you're always accessing even banks, then you're going to have a conflict and you're going to need 2 cycles to actually clear this thing. So it'll send through, one set of non-conflicting accesses. It'll pretty much bypass this tag unit because there's no tag check required for shared memory, because if the shared memory load says it wants that value, it's got to be in there, and it's on the programmer to make sure that it's actually in there. For the conflicted ones, we talked about this replay mechanism. So we need a way to do it again, right? Because you can't service them all in one cycle. So you can either stall the whole unit or you can replay it from a different position. Usually replay is the better option because stalling means that other warps sort of can't get in there. For shared memory loads, this is less of an issue, more of an issue for global memory loads. And then the question is, well, how far back do you replay from? Do you go all the way back to the I buffer that we talked about, or do you buffer somewhat inside the load unit? That's sort of a design decision that each individual core designer will make. And the issue is that we need the non-conflicting ones to proceed, and then we need the conflicting ones to replay sometime later, ideally 1 cycle later, in the case of shared memory loads. And we'll talk a little bit more about replay when we talk about global memory accesses as well. Okay, tag lookup is bypassed. The shared memory, like I said, is directly mapped. The arbiter will also schedule any writebacks. So remember all of this madness that was happening with the operand collectors and the register file. Remember that little example I walked through? Every time any unit is done and it completes an instruction that wants to write to the register file, which a load instruction will, I've got to schedule that write. I've got to tell the arbiter inside the register stage that this write is coming, so that write gets scheduled. And if it it sort of knows, in 1 cycle or n cycles, however long the access takes, is there going to be another write that's pending, for example, like, am I actually able to write in these cycles? It'll figure that out. And if it can't schedule it, then it'll wait. It'll sort of stall the whole thing and wait to schedule the write in the register file for when it's done. Okay, so then basically you'll use this crossbar network to figure out which banks you want to access on this cycle. Crossbar is an all-to-all connection. So each of the individual, thread lanes will want to access, it could access any of the banks, right? You remember when we were talking about bank conflicts, it was okay to have them all swizzled around as long as they were on different banks. This crossbar network allows for that. So that way every individual lane can access whatever bank it wants. The other thing about this SRAM, if we're doing it for the shared memory accesses, is that they don't actually have to be on the same row of the SRAM, each individual thread, because they can be accessing different, places in the particular shared memory bank. So there's decoders in front of each of these banks. And in this diagram, we're assuming that each bank is going to output a float. Okay, each bank is going to output 4 bytes. So each of these lines is going to be 4 bytes wide. These are all 4 bytes wide. And you can envision, a conflict-free access, lighting up all 32 of these banks and reading all of that data back out and then writing it back to the register file. Questions on this? Make sense? All right. And then the data gets written back, because ultimately once we read it out of the SRAM shared memory, we want to write it back to the register file. And of course, the active mask is always in here, right? Remember that active mask that is on top of the SIMT stack that's saying which threads are actually doing stuff. That mask persists throughout the pipeline, because when we do a write back, we only want to write back lanes that actually were active on this cycle. So that mask is, nominally in the pipeline register that's being sent down through each of these stages. Okay, so if we had to replay, if there were conflicts here, if we assume that the SRAM lookup is 1 cycle, which shared memory sort of guarantees, then we're going to have to send, the arbiter knows this because it picked out all of those conflicts, and then it will have to replay stuff. And more conflicts could be created, right? I could have a catastrophic case where every thread wants a different value from the same bank. In that case, I have a 32-way bank conflict. My arbiter, every time it's gonna go back and say, all right, well, like, all of these, who can go now? And it'll be like, well, only one of these 32 can go the first time. And then it will come back and say, all right, who can go now? And only one of these 31 can go next time. And it will keep doing this until it's cleared out the accesses for all of the threads in the warp. So, this sort of conflict creation process is like, it happens every time it rechecks things. It doesn't change, right? It's not like the conflict goes away, but the hardware still has to be there to check to see what the conflicts are and then sort them. Okay, questions on this? That's it for shared memory load. Is everyone sort of confident on how shared memory loads work? They're probably the easiest of the different accesses to the structure. The only real complicated piece is the conflict stuff and the replay, right? Other than that, you're just going to these SRAM banks, indexing them and getting the data out. Yeah.
So for replay, the buffer needs to be as big as the warp size, right?
So the buffer just needs to know what threads have not yet been processed. So it needs to know the instruction. So it has to, make sure it has the instruction, the addresses associated with it. And then it just needs to know who am I replaying, right? It doesn't, is that your question? It just needs a mask for every thread, right? If most things in the GPU pipeline can be amortized, just one per warp, as long as there's a mask associated with it, okay? Other questions? Okay. Yeah.
Do you have like lower top or low byte, like those sorts of instructions?
In the shared memory or in general in GPUs? You can load byte. There's a load byte instruction. You can load outward. There's actually long loads. So you can have one instruction load instead of just, you can load 128 bytes and fill all the registers are 32 bytes wide. Okay. So you could load 4 registers at once with one instruction. They're even, so the range of width on each individual load instruction is highly variable. If you have sub-word loads, then what would happen here is you would mask off some portion of it when you wrote it back to the register file. You're still going to read out 4 bytes. And then if you have a bigger word, it's going to take multiple, like loading floats from shared memory cuts the throughput in half, or sorry, yeah, loading 64-bit double precision stuff would cut the throughput in half because it's twice as much data. But it's possible. Again, in the same way that a traditional CPU cache would just read out some fraction and then mucks out the particular part at once based on the data type demanded by the instruction. Yeah.
This Etherpos as pipeline.
What's that?
It is pipeline.
This is pipeline. Yeah. Yep. Other questions? So in the ideal case, you can clear one shared memory load per cycle because it's like a cache hit basically. And if it's fully pipelined and you have a whole stack of shared memory loads, then you can sort of operate this at 100% bandwidth, right? What you really want to maximize the bandwidth here is that every cycle there's 4 grid bytes coming out of each of these banks to fill into the register file. And what programs usually do for shared memory is in the beginning, they do all these shared memory loads, which loads everything into the register file, right? So it'll load from the global memory, put it in the shared memory. And during that phase, you really want this to be at peak throughput because that's what's determining how long it takes you to load up your register file. Okay. Other questions? Yep.
Since this same banker is the cache as well.
Yep.
Maybe like allocate or deallocate shared memory and rest of the portion will be into the cache. So will that be partitioned to banks like a consecutive address
For
cache?
the cache, so you can think of it it's partitioned on kind of a row basis. So if the cache also gets 32 banks, but it's just they get different numbers of rows based on how much is shared memory. So it's not like they split the throughput. I mean, they split the throughput in time because sometimes you'll have shared memory load instructions using the structure. Sometimes you'll have global memory loads using the structure. But at an individual cycle basis, The shared memory load has the peak throughput, and then the global memory load has the peak throughput as well. Does that make sense? Other questions? These are good questions. Okay. All right, so that's shared memory loads. So let's do cache line reads. So now we're going to use this as a global memory structure. And the way that sort of this particular design works is you can read one cache block per cycle. We're going to assume in this example that we have a 128 byte cache line. So in the common case where every thread loads a float, this would be sort of peak throughput if you hit in the cache, if you had a fully coalesced access where they want the entire cache line. The way that this gets carved up, unlike the shared memory where, one thread could access one part of one bank and another thread could access a different part of a different bank, that's not really the way it gets cut up for the cache accesses, because we only have one tag associated with that whole 128 byte row. So that means that when we go access the cache, you get sort of one whole row of data out of this thing, okay? So there's this flexibility, like there's this demux in here, so I could potentially pick for each lane a different element in the SRAM array, but the cache accesses won't use this. They'll always just go grab one big line of data because it doesn't make sense to do it the other way because of the tag throughput. Okay, because we only have so many tags associated with the data. Okay, so the caches in real systems actually are sectored. So in 565, I think they also call this subblocking. Is that what they call it? What do they call it? Subblocking. So a sectored cache means that it sort of gives you the benefit of a smaller cache line without the tag overhead, right? As you shrink the size of your cache line, the number of bits associated with the tag and the number of tags associated with the data that's in the cache grows and increases the tag overhead of the cache. If you use a sectored cache, then you can have a sort of big cache line, in the case of a GPU, 128 bytes, but then you don't have to load 128 bytes every time from memory. You can only load a sub-block or a sector of the cache. In the case of modern GPU caches, the sector size is 32 bytes. That's also the quantum from GDDR memory. So when I go to GDDR memory and get something back, I'll get 32 bytes back. So, if I only really want 32 bytes of a cache line, I can just keep one tag and then only fill that 132 bytes of the cache line and then leave the rest of the cache line invalid until I need it. Okay. We won't talk about the subcoring, the sectoring here. It's sort of orthogonal to this problem. It changes the hit mechanics, right? Basically, instead of just checking to make sure the tag is there, you also have to check a mask to see if the sector you want for that tag is also there. That's really the only material difference. And when you fill 32 bytes instead of 128. Okay. Questions on that? So I'm going to go through the rest of this example, assuming we just have 128 byte lines, but the real caches are sectored. And the simulator that you use for this class also uses sectored caches to emulate what happens in a real machine. If you don't remember sectored caches, just go look at your 565 notes. Sub block, I think is what it's called. All right. So the load store unit is going to do this coalescing, this thing I just talked about before, and then said, oh, wait, no, it doesn't happen on shared memory. It only happens on global loads. That's what's happening. It can be done in different ways, but we can sort of assume for this example that it's done in the load store unit, figure out the minimum subset of tag accesses that we need. And then the arbiter will check to see if the cache has enough resources to handle this request. There are different ways you can do this. A conservative arbiter will check to make sure you have the miss resources before it goes and actually accesses the cache. Because if you miss in the cache, once you've said you're going to go, you got to go, right? And unless you have a replay mechanism, the arbiter is the only place where you can tell it not to go yet. So if you don't know if it's going to be a hit or not, you'd have to check to make sure you have resources to handle a miss. And if you don't, you have to wait until you do to process the request. And in this simple example, and the example that's described in the patent, that's how it works. Okay, so you can't actually, if you're locked up out of MSHR entries, then you can't continue to hit under at least this cache design because the arbiter will kick it out before you can even do the tag access. Right, so this thing, this pending request table, this is basically a miss status holding register, which allows the cache to miss multiple times, which is critical in GPUs because you need to have a huge amount of accesses in flight to soak up the memory bandwidth. So every individual core is going to have, you know, tens or hundreds, well, not hundreds, but maybe, depending on how many cores you've got lit up, you've got to have many, you know, 32-byte accesses in flight to soak up that peak memory bandwidth out of the system. And this pending request table is basically that. It stores the tag for the address that's in flight, and then it has, you know, basically merge entries to know how many different warps actually wanted this pending request, such that when it comes back, it can service all of them, okay? And that's what the pending request table does. So the arbiter at first checks to see if it's got the resources to handle this thing, even if it was a miss. If it doesn't, it kicks it back. If it does, then it allows it to proceed. It'll basically then go and do the tag check. So it'll check to see if the request hit. So this is because this isn't a shared memory access. This is a global memory access. Sometimes the values you want will be in memory. Sometimes they won't, because this is a true dynamic on-demand cache access. It does this sort of aggressive thing where it tries to schedule the write, because again, there's no way to stop the thing after this arbiter is done. So it tries to schedule the write in the register file, assuming that it's going to be a hit. And then if it's not a hit, it basically just cancels the write. Okay. So you can think of it as some kind of bit vector that it, you know, has some logic to say, well, if I didn't hit, I'm going to deselect the bit so that way I don't actually do the write. Because I don't actually know until the tag check is complete if it's going to miss or not. Okay. So you go and you check the tags, and again, the tag is sort of decoupled from the data SRAM here, which is common in cache design, but maybe you haven't really had to think about it that much before, because it may be that you actually have way more tag resources than you have L1D data elements, depending on how much shared memory the thing is using. And the tag can't be cut up. Like there's no use for the tag in the shared memory accesses. So the tag is like just for your L1 data cache. And sometimes you'll have way more tags than you need if your data cache is really small. And other times, if it's all data cache, then you'll sort of use the tag unit as much as possible. So then you go through and you check. So at this point, we sort of assume that it's going to be a hit. So this is what happens if we had a hit in a register file. This operates a lot like a sort of shared memory read. It lights up all of the banks associated with that hit. This assumes right now that I've got a fully coalesced access that hits across the entire row. So every thread is grabbing the data that it needed from that access, and then it writes back to the register file once that access is done. If you had a miss, so unlike the shared memory access, we need to do the tag lookup to see if you can actually proceed. So if the tag lookup failed, that means that you can't get the data out of the L1 data cache this cycle. So I now have to basically go through the miss path of the cache. So it will tell the upstream instruction that it did not finish and it needs to replay. And then it'll allocate an entry in this pending request table. That's what the PRT is, sort of like an MSHR. And then it will sort of proceed through the miss path and go to the MMU to initiate the access at upper levels of the memory, the low levels of the memory system. What does this imply about the cache? The fact that my MMU is right here. What does this imply about how the cache is organized or the design of the cache? What is an MMU doing? What's MMU stand for? Okay. Oh yeah, I wrote it there.
That means that the cache is shared and connected directly to the GDDR.
Not necessarily. So I'm thinking about address spaces. What does this mean address space wise based on the configuration of this miss path and the hit path? Yeah.
we're storing like virtual tags and virtual.
Yeah, this implies that the cache is virtually tagged virtually indexed, because I haven't done any translation before I go to the cache. Right? MMU is gonna do the translation because eventually there is virtual memory in a GPU all the way back to the very beginning of GPUs, even without UVM. You have to have some translation between the virtual addresses that the program has and the physical addresses of the machine. But this design, at least in early GPUs, did not put the TLB or any kind of address translation before or in parallel with your L1 data cache access. Right? You'll remember from 565 that there were different ways you can arrange your L1 TLB and your L1 data cache, right? You could have it in front, right? The downside of putting it in front is what? If I put the TLB in front of the L1 data cache, why is that potentially bad?
Every load is twice as slow.
Every load is twice as slow, but it takes twice as long, right? Because you have an extra stage, even if you hit in the TLB. How do you get around that? You do them in parallel, right? But this has a problem. What's tricky about this? How do I do them in parallel?
You have to make sure that you use the page offset bits as the index and the tag.
Yeah, you have to make sure the addresses line up so you don't end up with collisions that cause incorrect translations. But when you do them in parallel, there's just two things, right? There's tagged and indexed. If I did them in parallel, what does that mean?
You're comparing the physical tags.
You compare go ahead. Virtual index physically tagged, right? So what that means is that I can grab the index for where I go in the cache from the virtual address, so I can initiate the lookup, right, at the same time as I'm doing the translation. And I just hope to hell that I hit in the TLB, which most of the time you do, hopefully. And then by the time you get the tag out, you've got the tag translation, and then you actually have you can check the physical tag, right? We don't do this in GPUs because this is a very latency sensitive thing, right? And it causes problems with the way you map the address space with synonyms and, oh God, what's the other term? Synonyms and homonyms, that's right. And you have to be careful about the way the address space is mapped if you're doing it this way. In GPUs, at least in the early designs, everything down here was virtual. And for the most part, probably still is this way today. Now, if you had different address spaces, so in the early days, you couldn't run two different processes like on the same core. So it didn't matter that you would have, two different programs that wanted a different physical address for virtual address 0. That just wasn't possible because only one program would ever be running on one core at a time. Today, I don't know if they actually allow for this spatial subdivision, but they could. But then if they did, then you have to basically incorporate the translation inside the L1. Okay. There are L1 TLBs in modern machines, but in this particular design, the whole thing is sort of assumed to be virtual. Okay. Questions on this? All right. So the MMU is going to translate the virtual address to the physical address and then send it down to the lower levels of memory. And then there's this extra field that is here to basically tell us what, we don't want to go back into the pending request table and have to do a tag lookup. So we embed basically the identifier for what entry in the request table is associated with this particular miss. So that way, when it comes back, I can just directly index the miss table and I don't have to do another associative lookup on the miss table for this particular cache or for this particular access. And then as things sort of keep coming in and continuing to miss on that same line, so let's say that I had one warp that missed on address 100, and then I had another warp come in that also wants address 100, but the miss is still in flight, it'll get merged inside the MSHR. So it would know that these two warps both are going to be serviced by this request to address 100, and then when the request finally comes back, it'll wake up both of those warps and say, you guys can go, okay? All right. So then finally, when this thing comes back, so we just sent it out, we sent it to the MMU, translated it. Hopefully the L2 serviced it. If it didn't, then it had to go to the GDDR. In the worst case, if you're using UVM, it had to page fault it over from the CPU. So this could be like hundreds or thousands of cycles where we're sort of waiting for this thing to come back, but eventually it does. And then it sends a request to the fill unit to say, I got the data back. I'm going to put the data in this SRAM array. It uses that sub ID to look up what particular pending request I was responsible for. So we don't have to do a fully associative lookup again. And then the arbiter will use that to inform the ones that are waiting that, hey, your request is back. You can be rescheduled now. Now, the way that it does this is that it will actually lock the cache line. Because remember, there's all these warps like contending for this thing, and they're all just sort of flying off. Then maybe if your warp that is supposed to be replayed didn't get replayed right away, maybe that data that just came back in got kicked out, right, with LRU replacement, because this is a true on-demand cache. So to avoid that from happening, they lock the cache line so that it cannot be evicted until you know that the replay has occurred. So that way you know that the data can sort of come back and service the request. So then when the replay happens, we know that the line is going to be in there and it's good. And that's it. That's the mispath. Questions on this? Yeah.
I have a question for like how things might get handled with memory build lessons. Because I'm assuming like during the load and store unit or whatever it handles it, it might break it up into 2 instructions.
It would break it up into 2 accesses for the same instruction.
Oh, okay. So
Yeah.
there's no synchronization at the end to make sure that they're both, like if one had to access global memory and the other one had a hit.
Yeah. So that happens, right? You will have it's common, well, it can happen where like you have 2 accesses for one warp instruction, one is in the cache and one is not. You'll service the hit when it comes through, and it'll only write to the lanes that wanted that address, right? So again, there's a mask. There's always a mask, okay, for everything going on inside these pipelines because these are all warps. But then it'll know that the rest of the mask that didn't hit is still pending. And then an instruction it'll be like the unfortunate thing for the ones who hit is that they have to wait, right? So there's people who play games with this, right? Because it's like, this is like memory latency divergence. Like some of the threads will hit, some of the threads will miss, but all of the threads in that warp have to wait for the misses to come back. Because that instruction is going to be stalled up here. The whole in order pipeline is not going to be able to proceed even for those threads where the access was serviced. So it has to wait for the miss to come back. Then it will replay that instruction. It'll get the data that it wants for the other lanes, and then it will write back the other half of the lanes that missed. Make sense? So yeah, that's a good question. And if this happens 32, I mean, this is why diverged accesses are such a disaster. If it happens 32 different addresses, you have to replay this thing 32 different times. Thankfully, you probably miss, and then all 32 flight accesses are in flight, so it's not like it kicks you in the shins and makes you wait around. Like you probably initiate all the 32 accesses right away, but then you have to wait for them to come back before you can actually replay the instruction or clear the instruction, because you have to replay it every time the data comes back. Yeah, good question. Other questions? All right. Okay, so let's do writes. So what happens on a cache write? There's different write policies. So you remember from 565 that you can do all of these, different combinations of what happens when you write. Okay, to sort of remind you, the basic ones are, the basic things you need to decide are if you're going to allocate a cache line on a write, or if you're going to, or not allocate. So there's allocate so write allocate or write no allocate. The difference being on a write allocate, that means you actually allocate the line. On write no allocate, that means if you had a miss, you won't actually allocate the line. So writes will not be cached, right, in the cache. The other thing you need to decide is write back or write through. Write back will write it to this particular, write back means you don't have to write it all the way up, right? The whole hierarchy. This is where coherence comes in. This is where you get into trouble with coherence, because if you're writing back, then you're going to write to just the L1, you're not going to write to the L2. So the L2 copy is going to be stale, and you need a coherence mechanism to try to keep them up to date. And the way that the cache lines are handled actually varies between generation and varies between memory space. So there's different ways that this can be configured based on what access you're doing or what GPU you're using. So the older generations of GPUs used to write through and do write no allocate on writes in the L1 cache, meaning that you would if you had a write miss, you wouldn't put the data in the L1 cache at all, and you just write through out to the L2, and that would be it. Okay. For global data. For local data, so this is things like stack accesses that are thread private, where there's definitely no coherence problem because only one thread can access this data. It operated in a sort of traditional private L1 cache configuration, which was write back, write allocate, meaning that it didn't write it through to the L2 and it allocated the line in the L1 when the write happens. More recently, they have been creating more aggressive write policies on global data. So for example, in hoppers, the global data will be write back and write allocate. You can twist these. Some of the instruction modifiers will say, right, you can have an instruction that says, please write through or please write allocate. You can basically tell the thing to do it any way you like, but the default now is that it'll be write back with write allocate, so that way you can hit multiple times on writes, right? That's kind of the benefit. But the downside is that there won't be any coherence, right? So it won't actually write it through to the L2. So anything that you need to be visible to everyone else, there's no guarantee of when they'll see that update because coherence is not maintained. The data value will still go through. So it gets evicted from the cache, it'll get written back. But there's no guarantee that when the other cores will see that data because there's no coherence protocol in NVIDIA GPUs. AMD GPUs does support coherence with this policy. It's more expensive to do. They tend to do it in their APU parts. This is the integrated parts with the CPU because they want cache coherence between the CPU caches and the GPU caches. You want to do that. If there's a performance and area and complexity cost for doing it, the reason why NVIDIA GPUs don't bother with it is that most of the programs don't need it. They force the programmer to not do global communication by forcing them into this sort of thread block model, such that threads, thread 0 and thread 1 million never actually need read-write access to the same data. What else? Yeah, that's it. Okay, so there's basically all of the different same combinations that you can have. Write through, write no allocate, and write back, write allocate are possible in this cache, and it just really depends on the type of instruction that it gets sent. Questions on this? Do you guys remember these from 565, the different write allocation policies, et cetera? Makes sense? Okay, so if you've got a global write, there is a write buffer inside this thing. So both the writes to the shared memory and the writes to the cache will go through this write buffer. So it's just a FIFO. It'll go in there, and then if you bypass the cache, so if it's write through, write no allocate, then it's easy. You basically just go out and you send the request out through the store path when it gets to the front of the write buffer, bypassing the SRAM array entirely. If you are in write back mode, then it will basically write it to the line, okay, because it has the address, and then it will write it to the value that's in the SRAM. And if it's write back, then it doesn't have to write through, okay, if it hit. One optimization that GPU caches do if they are writing back is that if you write to the entire cache line, which is common, right? In CPUs, you don't usually write to the whole cache line, right? You think about a CPU, you write 4 or 8 bytes, the cache line is like 32, 64 bytes. So if it's write allocate, what does that mean? Let's say I have a write miss on a 4-byte access in a CPU and a 64-byte cache line. What does that mean I'll have to do in that CPU cache? What's the process? So I do a store word on 4 bytes. My cache size is 64 bytes. So what's the very first thing I'll need to do if I miss? Yeah.
Get 60 bytes.
You got to get the rest of the line, right? Because when you fill it and you put the tag in there, that says that all 64 of these bytes are good. You only have 4, right? Because your store is only writing 4 bytes, but you need to make sure that you have 64 good bytes. So when you have a write miss on a write back or write allocate cache in a CPU, the very first thing you have to do is go fetch. You have to initiate a read, right, from the L2, from the upper levels or the lower levels of memory to fill in the rest of that line, and then you can write your small portion of it. Because when you put the tag in there that says that whole line is valid, that happens all the time in CPUs because you never really write the 64 bytes all at once. In GPUs, if you've got a nice coalesced write, you are writing to the entire cache line in one instruction. So it's kind of stupid to go fetch it, right? You don't want to fetch the full 128 bytes, fill it into the cache, and then overwrite all 128 bytes because you know that you've got all the data, so they won't do this. So the special case where you have coalesced writes, it will not go fetch the data when it's write allocate because it doesn't need to. It knows it's writing over all the bytes. Now, if you don't, it still has to go get it, right? So if you have some diverged access, right, that is only touching half of the cache line, it has to go get all 128 bytes. If it's sectored, then it can be a little bit more intelligent because it really only has to go get the sector that you need instead of the whole cache line. Again, another benefit of sectoring, but generally, you still have to pay the cost of bringing in all that data before you can do the write. That's part of the reason why it was write no allocate in older generations before the cache was sectored, because then you'd have to bring in 128 bytes on every write miss if it was write back, and that's really not good form. And generally, GPU programs don't have a lot of this locality, right? Because generally the writes occur at the end of the program. All your stores to global memory will occur after you've sort of done all your stuff in shared memory, whatever, then you'll spew all the stuff out to global memory at the end. So there's not a huge benefit to caching all that because it's all just sort of streaming generally. Questions on this? Make sense? Yep.
The interactions between shared memory and global memory have to go through the register file, or can they go through?
That's a good question. In generations up until Ampere, which was like 5-6 years ago, they did. So you had to do a shared memory load, shove it in the register file. No, you had to do global memory load, I'm sorry. Get it from global memory, it goes to the register file, then do a shared memory store to put it in the shared memory. That's obviously inefficient. So they created direct loads in newer generations that will take it directly from global memory and put it into shared memory and bypass the register file. They also allowed these to be asynchronous, so you can sort of like queue up a whole bunch of these and then have a barrier to say, wait till all these are back before I keep going. Good question. Other questions? All right. Break, no break for you guys. Okay, let's go to texturing. So that was a sort of shared L1 and Scratchpad design. Many GPUs, including the sort of graphic-centric ones, like Turing, for example, which has the ray tracing, the early generation of ray tracing units, they would actually bolt the L1 data cache onto the texture cache because they already had this cache mechanism inside GPUs from the graphics days that was basically caching textures. And instead of sharing it with the shared memory unit, like I did in the previous design, they would just bolt all these accesses into the texture unit. And to understand, how this works, we really first need to understand what a texture cache is. Okay, what is a texture cache? Like, this is probably something you've not really seen before. You probably haven't had a lot of experience with graphics. So we're going to take a little bit of a tour into some of the graphic side of things to understand how the texture cache is working and how that impacts, the L1 cache that would be bolted onto the texture cache. You can also access the texture cache in CUDA, right? If you look at the CUDA API, there are special instructions where you can still load things through texture memory. And the super ninja programmers that want to use all of the on-chip SRAM as much as possible will use both the shared memory Scratchpad, the L1D, and the texture cache. But the access to the texture cache are a pain in the butt because you have to access things as though they were textures, which is sort of a different way to access data than you're used to from traditional C arrays or whatever. So there's this paper from the 90s that describes how a texture cache, could be built. The implementation of this is inside the simulator that you guys use for the cache, for the course. All right, so let's talk about texture mapping first of all. Let's do a little bit of foray into graphics. So when I'm trying to render a scene, scenes are 3D. Okay, basically you have all these models, you've got a camera, and then you're trying to figure out what models are inside the frustum of your view, and then sort of project that back onto the screen to render the pixels for the image. So that means that I have all this data that is three-dimensional, and then I need to color it, okay? So let's say I have a sphere, the 1 here, okay, or the L, I don't know what the heck that is. I looked at this from somewhere, I don't know where. But basically I have a geometric model of a sphere that's composed of what? What is everything in a 3D rendering scene composed of? Triangles, okay? This little thing is composed of a bunch of little triangles that represent the geometry of that physical sphere object. Now, if I want to put something interesting on the sphere, I need the equivalent of like an image, right? That's effectively what a texture is. It's basically an image that you take and you map onto a three-dimensional surface. So in this example, I want to map the smiley face onto this three-dimensional surface. And you represent these textures actually in 2D space. Okay, so every texture and everything you've seen in the 3D game actually has like a 2D texture associated with it. And they look ridiculous, okay? So for example, like when I was making sports games, the faces of the players, right? You have to like, the people draw the faces and the noses and the hair and everything. And then they have to put their face on there. So there's a little person in the room that's like taking an airbrush and trying to like make this person look like, you know, Rafael Nadal or whatever. And then at the end, there's an image, okay? And that image needs to get mapped onto the three-dimensional model of Rafael Nadal's face, okay? But when you look at it in 2D form, they take it and then they it ends up being like this big smushed thing. So it looks like this weird subhuman face, right? That basically maps all of the different coordinates on that, you know, on the model of all those little triangles that define his face to the two-dimensional texture. So that way, when we sort of do the math to take that 2D texture and plop it onto the model, it all works out and it looks like Nadal and not like some kind of monster, right? But, you know, it was kind of fun because you could like, oh, there's these little files of like, oh, Nadal, Federer, or Wayne Gretzky or whatever. And then you can sort of see their like exploded faces and they kind of look like monsters. So anyway, this one is, I should put one of those up there. That would actually be more interesting than this stupid smiley face. But this simple example, I'm taking this smiley face and I need to map it onto this 2D thing. Okay, so I basically need to figure out for all of the little triangles inside this little sphere, what color in this texture are they going to be? Okay, and that's kind of a complex process because it will depend on, you know, what particular color it needs to be, depends on the size of the thing, depends on how close the camera is. There's sort of all of these factors that you need to account for to figure out what the color of each individual triangle inside that sphere is going to be. And texturing is this process of taking this image for all intents and purposes and mapping it into a three-dimensional model. This is texture mapping. So model of a sphere, 2D texture, and this is what happens when they're mapped. So here I've sort of mapped it, and then there's some shading because you can see that like the edges are dark, right? So that there's some lighting happening here. This is part of what the sort of graphics pipeline is doing, is providing these kinds of different contextual colors. All right, so the game here is to basically find the coordinates of the samples in the texture and, you know, pixel, right? We talk about pixels on a screen. The little individual cell inside a texture is called a pixel. Okay, that's sort of the terminology there. There is going to be some spatial locality in these accesses because obviously, like, you know, if I'm rendering part of the mouth, like I'm going to access the stuff around the mouth, you know, from nearby threads. If it's sort of like every thread is a pixel on the final screen. And so there's definitely locality in these accesses. That's why the cache is important, right? There's lots of spatial locality, so we need to have a cache for it. And, you know, we don't just want to use the sort of traditional cache because it's inefficient in several ways, and we don't need that kind of efficiency for the texture cache, so they made a special cache for caching textures. The other thing we'll have to do is actually do some interpolation. So as we talk about this technique called MIP mapping, we'll see that we'll have to do some math to try to figure out like what color we should actually make this final pixel. So we're going to have a special sort of computation pipeline inside the texture cache as well to do some of this interpolation. Right. And so you want to do this with as little area and as little overhead as possible. You still want to capture this locality. That's sort of the big 10,000-foot view. So before we talk about how the texture cache works, I want to talk a little bit about this thing called MIP mapping. Who's heard of this before? Anybody? Not really? Okay, so what does this mean? So I showed you that texture or that texture of Nadal's face or whatever, right? That has a super high resolution. Okay, when you draw the thing, you want to do it in as high a resolution as possible. But it turns out that if you try to take a super high resolution image and then project it onto something that's very far away from the camera, okay, so something that's really small, like there's only a few pixels, right, that you get to represent this thing, and you have this super high res thing that you need to pick from, it ends up looking like crap. It looks really bad when you try to take a super high res thing and just, you know, sample it enough to you know, project the image back onto the screen, okay? And on the flip side, when you get really close to things, you really want a high resolution image because now it's taking up more and more of the screen. So all of the textures in pretty much all modern raster-based rendering pipelines, so any video game you've ever played, they take the highest, they start out with the sort of highest resolution that they need when the camera is right on the guy's face, and that's what we call level 0. And then they have this pre-processing step that essentially downsamples the texture offline. Okay, this is happening like when you're building the textures, not at runtime. So you can do a really high quality interpolation of what the colors should be for each of the smaller and smaller squares. And the way it works is they just cut each dimension in half, right? So level 0, if it was 100 by 100 size texture, level 1 will be 50 by 50, level 2 would be 25 by 25, and so on. Okay. And so you sort of bound it in how much space you need, but you can do a really high quality downsampling of this high resolution texture. So that way, based on how far the camera is, the idea is that I will pick the right level to render this thing with. So when it's really, really far away, I choose the lowest level, which in this case is highest level, I guess, which is level 3, where it's sort of downsampled the most. And then as the camera zooms in, it's actually switching textures to use ones with a higher resolution. Sometimes you can notice this in games if they've done a bad job, right? Like as the camera zooms in, like the sort of change, right? The sort of, it'll look one way, and then as you get a certain distance away, all of a sudden the model will have way more triangles, and you'll be at a different level of texturing, and it'll look better. But there's a transition phase, right, as the camera is moving in and out. So pretty much all textures do this to try to get really high quality images, regardless of how far away the camera is from the model. Now, the other thing that happens here is that, you know, there's going to be some distance, right? So I've got my, you know, player here, and I've got the camera here, and each of these layers would correspond to some distance from the camera. But oftentimes it's almost never perfectly on one of the layers, right? It's like, you know, level 0 was optimized for when he's right in front of the camera, but maybe he's just slightly further back than that, not far enough back to use level 1 yet. And that's often the case. So that means we're going to have to do some runtime sampling of both of those layers, okay, which is some kind of interpolation. That's what this little point is showing you here. This little point is saying, you know, I actually want like the texture that should be at level, you know, 0.7 and not level 1. So I'm going to take, I'm basically going to go and take 4 texels from level 1 and 4 texels from level 0, and then I'm going to blend those together to try to get the right color for that one point that I want. And so there's some hardware inside the texture cache that'll do this blending in, you know, for you, essentially. Questions on this? Does this make sense? So pretty much all raster-based rendering does something like this. And so what that means is that usually when I go render a texture, I'm going to have 8 accesses to memory. Okay, so where is this? Right. So you're basically going to go and you're going to grab 4 texels from layer 1, 4 texels from layer 0, and then you're going to do some blending based on the distance between the point you really think the point is to try to figure out what the final color value should be. So there's some nice spatial locality among the 4 pixels together that sort of, you know, surround the intersection point of level 1 and the 4 pixels together that surround the intersection point of level 0. Okay. Questions on this so far? Large can use blocks access, output pixel, so a bunch of small accesses, and they're usually in these bursts of 8 coming from 2 levels. So we want to exploit this locality, and we want to initiate the accesses as early as possible. Like we know we need these 8, so let's get all these 8 going because they're probably going to miss in the cache. All right, so that's the access pattern. That is what generally texture caches are optimizing for, this MIP mapping type of rendering. And there are some other design points that they're not concerned with. This is a GPU. There's a bazillion textures on here. I don't care how long it takes me to render any individual one. I just need to maximize throughput. So they don't really care about latency. So that means that the hit latency on a texture cache can be super long. So then you may ask, well, why the hell am I using a cache if it's going to come back in almost the same number of cycles as an L2 hit? It's a bandwidth filter. Okay, it means that you have more bandwidth now available. If you're hitting in that texture cache, you have more bandwidth available for misses from other things in the rest of the memory system. So even though it's not helping latency, it's still helping the overall performance because you're trying to, you're basically making good use of the memory bandwidth. Okay, questions? All right, let's start this. So this is an overview of what the texture cache looks like, and this is described in that paper that I pointed you to earlier. And the design is driven by, the things that we talked about. So basically, like, I don't care about latency. I want a super efficient and memory efficient cache, and I want to, make sure that I am capturing that locality that does exist upon all these texture accesses. So the way that it works is it keeps a tag array separated from the actual data array by this huge thing they call a fragment FIFO. And the fragment FIFO is going to be big enough that it's almost the latency of an entire miss to get from of a texture miss to get from one side to the other. So the way this works is kind of interesting because the tag array is actually going to run several cycles ahead. In most cases, this is like 70 cycles or something in the texture cache. It's going to run 70 cycles ahead of the data array. So it's sort of keeping track of what the future state of the data array is by the time this particular access gets to the end of the FIFO. Okay, so this has this nice effect where you can buffer up a whole bunch of accesses, right? And you don't need, a huge amount of MSHRs because that's the alternative in a usual cache design. You just have a huge number of MSHRs which are expensive. I'm not going to do that. I'm just going to have this simple linear FIFO with a huge amount of entries, and then I'm going to allow a huge number of misses to be in flight. And then by the time they get to the front of the FIFO, even if it was a miss, it's probably going to be back in the data array, and then I'm just going to get it from there. And if it was a hit, I could have went quicker, but there was no benefit. So I'm just going to delay the hits by 70 cycles. And again, it's this future state of the array, so the data doesn't even have to be in there for it to be a hit. It's just, hey, like, is it going to be in there based on the replacement policy I've used at the tag array at this point? Right. Questions on this so far? Yeah.
Data unused in some way to increase locality because we know the access pattern kind of.
Yeah, so there's a special swizzling, right, of these textures so that when they get laid down into memory, they call it Z mapping, right? So in memory, because usually what we'd have is like you think of a texture being laid out like this, right, in row major format. But because of this access pattern where you're going to grab 4 texels in a row, the way that they actually get mapped, this would be, if I'm looking at the linear address space, this is like 2 rows of the image. I would have it like this, and then I would have it like this, and then I would have it like this, and then this would be address 1, 0, 1, 2, 3, right? Because I know that I'm going to access these chunks, so there's this Z swizzling that happens with the texture data offline, because I know it's always going to be accessed in this sort of chunk of 4. That's a great question. And so when you compress textures, you sort of, well, there's also compression that happens on top of this, but when you arrange textures in memory, they're arranged in the Z pattern generally because of this very specific access pattern. Does that make sense? Because yeah, otherwise it would be kind of a disaster, right? If I had to jump a whole row to get these other 2 texels, now my locality is hosed. I need them to be prearranged in this Z pattern so that way I can maximize that locality. Great question. Another question here?
So effectively, this cache should have 100% hit rate, right?
By the time it gets to the end, yeah, it's gonna hit. Yes, effectively. Now, it takes a long time, but you still capture that locality, right? You'll capture this locality because it'll be like, so you'll initiate the first access to the Z pattern, right? And then the other three will come along and then you'll miss, right? So the miss will sort of take forever to get here, but then when it gets to the front, the next three are gonna also, they're gonna hit, right? They're not gonna have to initiate any other accesses. So it's a good way to sort of cheaply build a cache that can miss a lot and is not concerned with latency. Yeah.
So are those individual accesses or are they trying to load corpus data to Z pattern?
So
I'm thinking of a main conflict which tries to load the process.
right, so that, yeah, that's a good question. It's unclear whether they do this as like one giant 4-access chunk or if it's done as 4 different discrete instructions. Given the access pattern, it's most likely one instruction that's going to load the 4 things, and one anchor in the FIFO. But there will be reuse, right? Because you'll come back and you'll access part of that big chunk again, because when you load into one Z, you're going to get a bunch of Z's together, right? And then, yeah, so then the next ones will all hit. Makes sense? Yep.
There's no temporal locality in this cache, right? There's a lot of space.
You're not going to exploit a lot of temporal locality because you're going to render the thing once for every frame,
Right.
right? So it's mostly just, I rendered this Z, I need to render the next Z and the next Z because I'm going to be rendering this stuff over and over. If you repeated, there is a potential for temporal locality if my whole screen is a bunch of little faces, right, that are all referencing that same texture, then every time you re-render the face, you're going to get temporal locality. But generally, I mean, that happens, right? Like if you've got a building that's got bricks on the wall, there's probably one brick model loaded, and it's just reusing that texture over and over again. So there would be a chance at spatial locality if you've got repeated objects in a scene.
Because
Temporal locality.
if we had a lot of temporal locality, then this would be suboptimal.
Yeah, it's not great because it might get kicked out by the time you come back. It's mostly designed to capture the spatial locality and the access on one individual. And it's not that big, right? It's like 16K. So you're only really trying to grab the next 16K of this texture and sort of move it along. And by the time you get to unless you're just rendering the same thing back to back and it fits in 16K, you're probably not going to get a lot of temporal locality out of it. Okay, good question. Other questions before I let you go? Yeah.
You guarantee you won't get a big
Yeah, you can, because it's running ahead. You can guarantee that the state of the tag array is synced to the state of the data array when it gets to the head of the FIFO. And the reason why you can guarantee that, I haven't discussed this yet, because in the MIST path, we actually have a reorder buffer. So if all of the accesses come back in order, then you can do a thought experiment to say that, yes, it should be guaranteed, because I know that like if the tag array is the exact same size as the data array and all your memory accesses came back in the right order, in the order that you sent them out, then it will be reflective of whatever it is at the only thing the tag array is being used for is to decide whether you need to miss or not. That's it. By the time you get to the front of the FIFO, it's assumed that that data is going to be in the data array. If you size it appropriately, you can guarantee that. Makes sense? And you guarantee the order they come back in. That's why we have a ROB here to try to make sure that, because the memory system might reorder stuff, so you may have. And we'll talk about this next time. Good questions. I'm gonna let you go. All right, fine. Last one.
How do you decide the size of the fragment?
Yeah, it's dependent on the relative latencies, right?
Yeah.
You've got to make sure that it's sized correctly, or else it won't operate.
But
Right.
do you really have a guarantee on the latency? Sort of
On texture accesses, you can bound it, right? So you just have to make sure that it's not gonna, you're not gonna fly off the handle. Now, is there some kind of mechanism you could also look, so if you made it the right size for the maximum number of cycles it's going to take, then that seems like a very tricky game to play, right? So there's also mechanisms in here to make sure that the thing has been build before it actually proceeds from the head of the FIFO. So if, for example, it took longer than you anticipated, you got to the head of the FIFO, but it has not returned yet, you can stall it, but then you stall the whole thing, right?
Because for MSHR design,
Right.
you can use the little flow expert.
Right. Correct. Yeah, you can get the right size here, but again, it's be a range because it's going to be a minimum time and a maximum time that the memory access takes. And none of this is page faulting. Like all these textures are loaded into GPU memory. It's sort of guaranteed to be in the HBM when you go there. The only question is, are you going to the L2? Are you hitting the L2 or are you missing in the L2? And then obviously there's reordering and like priority things that happen in the rest of the memory cell that could slow you down. Okay. All right, good. Good to have you back. Let's talk Thursday. I'll see you then.
That's